Science Foundation Exceed Systems. And then we'll have a break 1 to 1:30, that is Eastern. And then we'll have presentations from Todd Gamblin from Lawrence Livermore National Lab. I indicated in my talk yesterday, we have been working very closely with SPAC, making all our MVAPICH library distributions available through SPAC. So we have worked with them in the context of like, how do you handle binary distributions in SPAC? So that's what he will be talking. The following talk will be then from Red Hat. We have been working with Red Hat for many years to integrate MVAPICH into their enterprise Linux. So Hong Yang will be sharing some of his experiences there. Then, like the previous years, in-person meetings, we always have like a lot of students also we invite through National Science Foundation's travel grant. Of course, this time it is virtual. The students are attending virtually. So Professor Alan Schussman, who directs the one of the NSF directorate, he will be talking about the cyber infrastructure research, learning, and workforce development. And then we'll have a presentation from Xscale Solutions on how to accelerate HPC and DL applications using DPUs and also checkpointing. The following talk will be from Ohio Supercomputer Center, jointly with OSU. As some of you know, we have a network analysis monitoring tool called INAM. So it has been deployed at Ohio Supercomputer Center for many years. So we'll be trying to give a live demo and also share some experiences. And then in the end, we'll have, just like yesterday afternoon, we'll have short presentations from some of the MVAPICH members going into more details of some of the future things, what is coming up. And then in the end, we'll have an open mic session. As a tradition, the open mic is free for everybody. You can talk about anything, what you need from the group, give us some challenges, your experience regarding what works and what doesn't work. So we'll do that at the end of today's. And I believe all of you have been familiar, but we are like using the Zoom webinar. We also have a Slack channel in parallel. So for every session, we have separate Slack channels. Please feel free to post questions there. You can also post questions in the Q&A box. And as we are progressing with the program, we are also collecting the slides, PDF slides, and linking to the program. And also the video recordings will be cleaned up and then will be linked to the website. So with this, let me thank all our sponsors listed here. And we'll get started with today's program with the keynote talk. And let me try to formally introduce Dr. DeRose. So Dr. Luiz DeRose is not new to the HPC community. He has been there in this community for many, many years. Currently, he's the Director of Cloud Engineering for HPC at Oracle. Before joining Oracle, he was a Senior Science Manager at AWS and a Senior Principal Engineer and the Programming Environments Director at Cray. Dr. DeRose has a PhD in Computer Science from the University of Illinois at Urbana-Champaign. He has more than 25 years of HPC experience and a deep knowledge of programming and middleware environments for HPC. Dr. DeRose has 8 patents and has published more than 50 articles in scientific journals, conferences, and book chapters, primarily focusing on compilers and tools for high-performance computing. So with this, let's welcome Dr. DeRose for his keynote talk.
Thank you very much. It's really a pleasure and an honor to be here. I really appreciate the invitation. And so can you,
yeah, it is coming up, but in the presentation mode.
Put in presentation mode here and
yeah.
All right. So yes, it's I'm really excited about. Thanks for the introduction. I spent most of my career at Cray. Sometime even before Cray, I was 5 years at IBM Research, but all this time on HPC. So more recently, I decided to move, basically learn more and being able to provide some of my experience on the cloud. I moved to Oracle this year. It's a quite exciting place, and we're doing a lot of interesting things, and I'll talk about some of them today. So basically, the outline of my talk is we will start with basically trends in the computer architecture, right? How what's going on, what happened in the industry in the last many years, right? But then the most important point here is the impact that these changes had on both software development and software from the system side, so basically programming and middleware environments, but also the impact on applications, right? And then I will switch gears and talk a little bit about HPC on the clouds. And in fact, this is one of the reasons why I decided to move to the cloud or move to a cloud vendor. And then I'll talk about what Oracle provides on the clouds, which I think is quite exciting. And then we'll finish the talk at that, right? So this is a plot that has, in fact, it was done quite a while ago, but I think is very interesting, right? So it was done, this one was done, in fact, in 2010, and showing what was going on, right? So it's basically, we can see clearly that in 2005, the technology reached kind of basically a barrier there, or a wall, let's call. And I mean, one of the things you see on the top line, the red one, you can see that because I mean, based on Moore's law, the number of transistors kept increasing, right? And it's interesting because Moore's law, some people thought about in terms of performance, but the reality is it's a number of transistors. And during basically 95 to 205, we're just riding on that, right? Every other year you had a much faster system and whatever. But you clearly see this change in 2005. And with that, you see the number of cores kind of start to increase. That's when we start having many cores, dual cores to what we have today. We have systems with more than 100 cores, processors, but then everything else kind of flatten out, right? So the impact of this is that, as I said, Moore's law was talking about the transistors, and as they kind of shrink the chip area, they could add more and more and more transistors and make things much faster. There is also a Dennard scaling law that basically says that performance per watt will double every 2 years, and that was happening up to physics kind of got in the way, right? So the scaling no longer applies, and that's basically what caused this flattening of frequency, flattening of power, flattening of single thread performance, right? And but I mean, the number of transistors kept increasing, and but that wasn't the number of transistor count alone is not enough to keep adding, sustaining the microprocessor development, right? So as I mentioned, there were too much heat, too much power being consumed, and that needed some change, right? More recently, in fact, so again, we have these 35 years of microprocessor trends, And there was a new plot by Roop, and that showed basically added 2010 to 2017, and you see exactly the same trends, right? And you all see things like at this point we're already seeing that what I mentioned, there were processors with more than 100 cores, and there were like lots of experience, lots of different technologies that had to adapt to this major change in the industry, right? So, and basically the industry response was that we start to have a multi-core, many cores. GPUs start to be popular on HPC. We start to have all kinds of vectorization. And so that basically created a huge diversity in what was being provided, right? So in the past, things were simple, right? And in some sense, we kind of, some of us got kind of, let's say, used to this, like just develop for the same architecture and keep getting faster processor and faster processor. So everything was simple because it was pretty much linear, right? So now our one dimension, right? So with all this change, things became much more complicated, in particular for people that do programming middleware environments. One example is, so if you think about, and like I said, I spent quite a bit of time in developing programming environments, and things changed quite a bit with this new trend, right? Because in the past, what we used to do was basically go and keep optimizing for that particular architecture. There would be a few changes and whatever, but we had one focus, right? Coming about in 2010, when Oak Ridge decided to use GPUs on HPC, things start to change quite a bit, because now if you are thinking about developing software, now we have two completely different ways of approaching or using the processors for HPC, right? So GPUs and CPUs, and I will talk a little bit more about that. Things kept growing, and now we have ARM. We have AMD has a very appealing, a very interesting processor. They in fact have both CPUs and GPUs. Intel kept providing very competitive, very interesting processors. NVIDIA is very strong on the market. Like I said, ARM by itself, it's in fact a designer of the architecture, but then you have even different providers, right? So you have Fujitsu, you have Ampere, you have Marvell, and many others. So if you are, or for us, developing system software, that's what happened was now you have to split your focus in many different options, right? It would complicate. If you are doing that for one of these vendors, that's still not a big deal, because if you are Intel, you develop for Intel processors and don't worry about NVIDIA. If you are on NVIDIA, you develop for NVIDIA, you don't worry about the other one, same thing with ARM and AMD. If you are outside, and like I said, my previous life, that was what we were doing, providing processors for all options that we could, because at the end of the day, it's almost like a competition, right? You don't know which will be the best processor. So we want to support as much as we can, but that puts a big toll on resource for development, right? So that was one of the facts that's quite interesting there. I mentioned about the GPUs and CPUs, right? So again, that's also created some interesting, to say the least, issues, right? So again, before 2010, basically most people were just using CPUs and working with that, right? And there is a big difference in the way that you use CPUs or GPUs on HPC, right? And in fact, and that also created quite a bit of change. One of them was with the emergence of new programming environments, programming models, right? So with GPUs, people had CUDA, and then there were quite a few initiatives to try to raise the level of abstraction. And I myself was involved on the creation of OpenACC. So in fact, even before OpenACC, there were PGI had their own set of directives. Cray had directives for GPUs, and there were another company that even escaped the name that also had directives. So we end up trying to get directives to access to use the GPUs into OpenMP, but that process was kind of slow because OpenMP is a big committee, so we end up creating OpenACC, but then OpenMP had their own directives, which also kind of created two different standards that complicated life. So again, all these changes in the microprocessor technology created a lot of changes in the industry, right? In the software development industry. It's kind of, I always mention that if you're doing research, this last decade and the future looks quite interesting, right? It's really challenging. There is a lot of stuff things changed quite a bit, which is quite interesting. If you are in the market to buy a system, or if you are developing system software, things are not that simple, right? So that was a quite interesting change in how we do things, right? Another thing that happened is, of course, the hybrid programming, right? So hybrid in terms of I want to mix CPUs and GPUs. There is quite a bit of if you can mix the two efficiently, and again, at Cray we built libraries that would use the power of both together. In fact, scientific libraries was one area that you can do mix of CPU and GPU and add performance. So there are, like I said, there is quite a lot of stuff that you can do, but the issues on or the main problems are regarding resource to do all the work that one wanted to do. So this is on the software side, on the system software side. So on the application sides, it was also quite a big change, right? So the main one is architectures were optimized for the most widely used applications, which are not necessarily the HPC one, or mostly commercial and gaming. On the GPU sides, now with AI, people are also optimizing some GPUs for AI. But other than that, mostly the architecture, the applications had to adapt to the architecture. So, and of course, the application requirements are not a one size fits all, right? So you have different needs, and there is no single application no single processor that will be the best. And to complicate, right, as the applications get more complex, this match is even harder. So NERSC, a while ago, that was 2014, Katie Antipaz and team, they have this quite interesting report on the workload analysis, and that was on Hopper, which is, I think, like 2 or 3 generations ago on the NERSC supercomputer sites. But that's a very interesting distribution, right? So you see again that the diversity of codes that are running on a big supercomputer sites is huge, and even on some codes. I mean, the top one here on the right, you see CESM, which is basically a community earth science model from UCAR, and that code by itself is already kind of basically looks into atmosphere, land, and ocean. So even itself has different requirements, right? So with this diversity, it's really hard to focus on a single processor or a single system and make the application run better there, right? So there is also the issue about the programming model for these applications, right? So one of the key things is the fact that with this diversity and multi-core, what we saw was now you have to better utilize the systems. You need to adapt your application. So MPI is still the dominant way of communication. So all of them tend to use MPI between the nodes, but to use the others, so people are, so now we have these wider nodes, so there are still applications that can use MPI on the nodes, but a lot of people have been trying basically the hybrid approach with OpenMP and MPI. And then you need to look into vectorization, and the vectorization could be just on a single CPU with SSE and AVX and SVE. But also you can think, if you're doing hybrid CPU GPUs, you need to think about the GPU itself, right? So the other complication was that as nodes were getting wider, so now the memory bandwidth cannot keep up. So then we start seeing kind of it keep coming back is more complex memory hierarchy, right? So KNL was a big example on having the two different memories, and if you were, I mean, there was the option of using as a cache, but if not, then there were issues about how do you adapt how do you decide what should go in the fast memory and what should go in the regular memory, right? And that's also quite good for research, but again, for application development, for programming environment development, that adds complication, right? So with all of these, we see that now thinking a little bit also on the supercomputer centers and looking at on-premise HPC workloads and the challenge, right? So one of the main challenges is capacity planning. So on capacity planning, so what happened is a typical HPC center will have a system for 3 to 5 years, and you need to look into what's the best processor for the workload. And but then if you have a diverse workload like I showed for a place like NERSC, for example, and other sites, that's already a big problem, right? The other big issue is the provision to, so do you plan for the average use or do you plan for the top use, right? And if you plan for the average use, then you have a lot of people that will be waiting for a resource, computer resource, right? If you plan for the maximum use, then you have a lot of, you may have idle resource, which in some sense is a loss of return of investment, right? So, and then there are other considerations like all the security issues, all the basically keeping up with the data center. There is lots of problems there. One of the big ones is on this scenario of 3 to 5 years of a system, there is this big issue about cost of lost performance, right? So, and that was, in fact, TAC had a report on that. We ourselves have done some analysis on that, right? So let's think about, okay, in 2016, the Oracle Cloud had Intel Broadwell, right? And on the right side here, you see the number of production jobs per year. So basically, 16 they have Broadwell, 17 they had Pascal from NVIDIA, 18 they have Skylake and Volta, 19 they had Naples, and 2020 Rome, Ampere, and Ice Lake. And as you can see, as these new technologies or these new processors were coming, you see that the number of production jobs kind of kept increasing, right? So if I look at this, rough calculations at 3x, right? So basically I started SCO at 1.5 million, and then I'm close to 5 million. So 3x is basically, if you think on a 5-year scale, or the 5-year plan, is quite a bit of performance that's left on the table. So that's an interesting result too. So that leads into HPC in the cloud, right? So one of the things is, based on everything that I said, at least for me, it's clear that the users need a infrastructure that can adapt to their workload needs, instead of having to try to keep adapting their workloads to the new, or their programs to the new systems that they have, right? You see in some of these centers, people move to GPUs, or people move to KNL was a big example, right? So a lot of people invest on the KNL, but now they are basically KNL is no longer, that kind of architecture is no longer in place. So now people are using, going back to just plain CPUs, or they're going to GPUs. So there is all this kind of change, and the people on the application development have to adapt to that. One of the facts on this is that sometimes you have two applications, right, for the same thing. You have to do the port for GPU and the port for CPU, which is also kind of costly, right? The move to the cloud has, I mean, the cloud is around for quite some time already, right? I would say about 15 years. And HPC is pretty much one of the late moving workloads to the cloud. Partly of that is, first, people have a lot of investment in infrastructure. And the other one that's quite important is the initial cloud performance. So HPC is very sensitive, right? And the initial cloud performance for HPC was not really good, right? And mainly due to virtualization, network, and other things like that. So now there is, again, the cloud evolved quite a bit, and I will talk a little bit at the end about the Oracle Cloud. So evolved quite a bit, and HPC is moving towards that. One of the first adopters are basically CAE and bioscience, right? And if you look at the market itself, Hyperion Research basically does a lot of a lot of goods publications on forecasts and things like that. So they forecast the HPC market to be at 46.6 billion by 2024. So, and Intersect 360 also forecasted, they forecasted like the cloud to be in 3 billion by 2023. Hyperion kind of see by 2024, the cloud to be at 8.8 billion. And the growth, the aggregated growth over these 5 years, the growth on the cloud is about 17%, more than 17%, while that same growth on on-prem is less than 7%, right? 6.9%. So you see that the cloud is really growing quite a bit the HPC on the cloud is predicted to grow quite a bit in the next 5 years, right? If you see that's the same result from basically the presentation at ISC this year. And you see the verticals here, like I said, bioscience and CAE were the first adopters. Bioscience is already over $1 billion, over $1 billion in 2019. And the other interesting thing is if you look at public sector, and I am defining public sector here as defense, government labs, universities, and weather. That is the largest growth, is a growth of about 20%, above 20%. So that's quite interesting. So why HPC on the cloud is better than on premise, right? So the first one goes back to what I mentioned before, right? So you can run on the latest generation. You don't have that loss of performance because you are stuck to a single platform. The other one is the pay only for what you use, which goes back to that decision on, do I provision for the average or do I provision for the top? In a lot of places, you see quite a bit of a variation on the usage, both on academic work as a research, as in commercial work, right? So you have the peaks and valleys. And then there is the whole being into the data center business. That's always a problem, right? So at the end of the day, you want the system or the infrastructure to do your work, but now you have to build your own facilities. I remember starting when I started even at IBM, but during my whole career, many times people had to wait for a building to be built so they could put the system over there, and which also kind of is a loss, a big loss, right? So this is saying pretty much the same thing. How do you benefit from moving HPC workloads to the cloud, right? So one is cost. Cost is, in fact, it's quite interesting because people have this impression that the cloud is much more expensive. But the reality is, if you start to put all these indirect costs that you don't, or you mostly don't see right away on the cost of the data center, the IT costs and a bunch of other costs, end up being, when you start looking at that, that's one of the things that's really discarded right away because it's not a problem. The capacity is really a big win, right? Because I remember when I was starting, and we created IBM and NCSA and University of New Mexico. We created something called the Linux Cluster Institute. And a colleague of mine from NCSA, so my area of research was performance tools, right? And I was a postdoc for Dan Reed for some time. And then at IBM research, I was doing basically performance tools. And one of my friend from NCSA once told me, do you know what? People will invest much more time in trying to figure out how to cheat the queue than trying to optimize the program. And which for me was very discouraging because, I mean, I thought, oh, performance tools, right? So we need to get the best performance and whatever. And if you look at that and say, well, it's true, right? So if instead of running my program once a week, I run twice a week, I get 100% speed up there. So, so that was a quite interesting thing that I learned. Although I kept doing performance tools, so didn't discourage me that much. Flexibility is another issue, and of course, performance is another of the games, right? So I'll finish the talk with a little bit of what we have on the Oracle Cloud infrastructure, which we call OCI for short. So interesting that, I mean, a lot of people think Oracle and think database, but Oracle has been in HPC for quite some time, right? So basically, initially, they acquired DAC Digital in 1994. In 2010, they acquired Sun and got a stake on Mellanox. And Sun, in fact, on their database is still being used inside of some at Oracle, right? In 2016, Oracle decided to invest on the cloud. So in some sense was kind of a late arrival, right? So it came basically 10 years later. But that was also good because they could look into what was there and how can we, in some sense, you think about how can we avoid some of the mistakes and fix them and develop from there. And then every year, as I mentioned, in fact, in the past already, so there were some new technology being added. One of them, the most important one, I think here is RDMA that came in 2019. But one of the big differences in the Oracle Cloud as compared to other ones is that we really focus on bare metal, right? So, and the idea here is that the user will have direct access to the hardware. So there is no hypervisor, no single, basically everything is single tenancy. And that removes the jitter, removes noisy neighbors. So you don't have performance loss here, right? So the other big thing about Oracle is, I mean, as I mentioned, right? So Oracle DNA is in database. So they do understand quite a bit about storage, right? So so adding the storage expertise, adding the bare metal, and then I'll talk a little bit about the network later on, but that makes Oracle Cloud quite different, right? So I think the idea of coming late and looking at the whole package and how can we avoid mistakes and how can, I mean, one of the big ones is the virtualization, and I'll talk a little bit more about that. So the Oracle Cloud has, in fact, we provide AMD Apex systems. Now we already have Milan installed. Of course, we provide Intel systems. We have the latest one, Ice Lake. We have Ampere ARM systems. And of course, we have GPUs. And the GPUs are all bare metal. Not all, but they I mean, we also provide VMs, but the focus for HPC is really on bare metal, right? So how about the network? And I mean, one thing that's interesting is assume that your MPI task is a marathon runner. What should you really care about? Should you care about the fastest guy? Should you care about the average? Or should you care about the last place finisher? And of course, I mean, in this community, I don't think I need to explain. But yeah, we really care about the last place finisher, right? And it's interesting. This I saw on the web. This is Fran Drotz, 72 years old, finishing the Boston Marathon. Took 9 hours, but finished. So I don't think I can do a tenth of a marathon. So I really envy this. So the network, basically, we focus on the low latency and high bandwidth. So the Oracle Cloud, basically this is RDMA over converted Ethernet, so called Rocky V2, and basically the servers are connected directly into the network, and the idea here is really to avoid jitter, to avoid basically so you have the same really feeling as on-prem, right? And the putting together these, the bare metal and the network, not having so one of the big problems in the first attempts of using HPC on the cloud was really the virtualization of the visualization is not synchronized, right? So as you increase, then you have more and more jitter, and the jitter will create the problems on HPC codes, right? So having a low latency network that's predictable and the bare metal makes things quite different, quite more positive for HPC. So underneath there is a physical layer that's basically is not oversubscribed and has up to 250 gigabits per second bandwidth. And like I said, a predictable low latency. I'm not going to talk much about storage, but again, like I said, databases in the Oracle's DNA. So it's pretty, so storage was well taught into the Oracle Cloud, right? So it's pretty straightforward to deploy parallel file systems, and you can choose between a variety of file systems, and then you have basically you have NVMe, and you have block storage, and you have other options. So if you look at the usage of the cloud, so you can see 3 different ways, right? So one is you can just go 24/7. You can do bursts, and that's in fact one of the strong components of our cloud too, is this hybrid mode between you can have kind of a use on-prem, but then if you run out of resource on-prem, then you just burst to the cloud. And then there is the variable workload that you just use the cloud when you need. OCI, in fact, has a big support for hybrid cloud, right? So we have many public regions but we can also have dedicated regions that is co-located with the data center if the customer prefers that way. And but the big deal here is the scaling out, right? The outscaling, basically to do the bursting to the cloud, right? And the burst can be both if you are 24/7 on the cloud, or as I mentioned, hybrids, clouds, and on-prem. Quick, I have 1 more minute before questions. So those are results that basically show that, again, because of the bare metal and the network, our results are very similar to on-prem, right? So to the on-prem system. In fact, this one is quite interesting because it's a comparison. If you look at the left side, right? So it's a comparison of the Oracle clouds, that's the red one here, and some on-premises systems. And the one at Kyushu University has, in fact, this exactly the same configuration. And we see we got exactly the same results, right? So that, again, shows that not having the virtualization, having bare metal, and the network, low latency, basically provides similar results. There are, of course, systems that still provide better numbers, like Osaka, and there are other ones that provides not so good numbers. And the right side, I don't really like to compare with competition, but just saying that, again, because of bare metal, the performance, and this is open forum, so pretty big model, and you see, again, the performance very, very good there. So, what I try to present today, so basically is the trends in microprocessor technology have been influencing HPC a lot, right? I mean, like I said, we no longer have a dominant processor architecture, which basically complicated quite a bit the life of the application developers, the life of system software developers. So this architecture diversity is quite exciting if you're doing research, but not so much for if you have to select a system for on-prem, and of course, not so much for system software developers. Right? HPC on the clouds is growing. It's predicted, the forecast is to reach close to $9 billion in the next 2024. So we're talking 3 years from now. On the Oracle Cloud infrastructure, the view was to first look at how we can improve from problems in the past, and how can we create an infrastructure that can adapt to the workload needs of the users, instead of having them trying to figure out how to adapt to their workloads to a system, right? And change things. So I still have, I believe, a few minutes for questions. Thank you.
Thank you, Dr. DeRose. That was an excellent keynote. I really appreciate that. So we do have a couple of questions, and I will read these for you.
Okay.
So we have a question on Slack that reads, thank you, Dr. DeRose, for the nice keynote. Can you tell us more about performance analysis in the cloud? What is Oracle's solution for HPC performance analysis in the cloud?
So I mean, performance analysis, do you mean in terms of I have an application, I want to see how it's going? Then it's pretty straightforward, right? Like you do on-prem. You just build your cluster. In fact, creating a cluster on the OCI is pretty straightforward, and run that. If you're saying performance analysis in terms of, oh, I am a researcher in performance analysis, or I'm a developer that are building tools, then basically the clouds tends to be much more like an infrastructure than again, like an on-prem system, right? So what you do is you build your cluster and you bring the tools that you want to use, right? So it's not as much as like say when I was at Cray, we were building a performance analysis tool that we would ship with the system. Here, basically, the users will bring what they need. But I mean, tuning your code is just like on-prem, right? So if you want to tune the code, and because it's bare metal, and in fact, on the example that I showed from Kyushu University, compared to Kyushu University, it's pretty much if you tune for one, you tune for the other, right?
Okay, that sounds good. Thank you. So we have another question on Q&A. So this is by Kenneth Host. One of the big differences between on-prem and cloud infrastructure for HPC is that on-prem systems provide way more than just the hardware. For example, a catered central software stack next to a user support team. Is that also provided by cloud providers?
So again, the on-prem, I mean, on the cloud, you in fact, you can have, there is the model that you have a system integrator in between the cloud provider and the user. And the system integrator, so if you think about, again, let me use the Cray example, right? So you buy a Cray, you get all the software stack that's provided by Cray. In one hand, it's good, and the other hand, sometimes you want to use something else and it's not there. So if you buy a cluster, you pretty much have to bring your own system software, right? So then you have sometimes the HPC center is the one that takes care of bringing the system software. So in some sense, with the cloud, not really change that much, because you can still have the same group that's doing that bring into the cloud, right? So you get the cluster, you get your module load, and you load what you want. So in fact, it's interesting because in some place, one example that I think is quite exciting, quite interesting is on-prem. I used to interact with the guys in Finland, right? CSC Finland. They moved their on-prem sites way north to take advantage of the low temperatures, and nothing really changed from the user perspective, right? So the user perspective, where the system is, doesn't really matter. So again, the same group that does this for the supercomputer sites can continue doing this for the cloud.
Sure, excellent, thank you. And I also have one question. So you also have background from academia. You have worked at NCSA as well. So how will this, emergence of HPC in cloud, affect open source software development? Because, university researchers, students, they don't have a lot of money. So are there any programs, from, let's say, Oracle cloud infrastructure that support this kind of, research and development?
Yeah, so our Oracle Clouds, Oracle has a research collaboration And yeah, so, and again, on the Oracle Cloud, open source is a big thing, because like I said, the idea is we provide the infrastructure, but the more open source, the more tools that one has to use, the better, right? So yeah, so Oracle has a research component. So if there is any interest or collaboration, just contact me. I can point to some of the groups that are doing research collaboration. We do, in fact, we're planning supercomputing, and we will be showing some of the research activities that we have been doing collaboration with universities that are using the Oracle Cloud and things like that.
Okay, excellent. So with that, I thank you again for your excellent talk. And in the interest of time, I would move on to the next talk. So
all right.
one more time. Thanks.
Thank you very much. It was a pleasure.
You're welcome. Thank you. So with this, we move